Assalamualaikum warahmatullah. Welcome to the third lecture of mechanical vibrations. In the last lecture, we discussed about the introduction of mechanical vibration, what are the elements of vibrating system, mechanically vibrating system, that is spring, mass, damper, and how do they contribute to the vibrating system, what is our role and function of individual element in that vibrating system. So in this lecture we will formally start with the calculation, mathematical modeling. We'll start with the basic one and then we'll slowly move towards advanced techniques. So we know that there are three fundamental elements, that is spring, damper, and mass. So we will see how, obviously in the real world vibrating system, there's not one spring. There are multiple spring, multiple things that may act like a spring. In the real world, there may be multiple things that will act like a damper. In the last lecture, we see the example of pendulum. So in the pendulum, if the pendulum is vibrating to and fro, so there will be resistance at the connection here, and there will be resistance because of the airflow. So both of them will be acting like a damper. So we have to, obviously we can't use separate equation for each damping contributor. So what we'll do, we'll try to find the equivalent amount of damping for the whole system. So in this lecture we will see that one, how we can do that. Let's make it small. So let's suppose, starting with spring, if there are many springs that are parallel to each other. So before going over that, we know the spring is equals to, the spring force is equals to kx. Let's call it Fs. So let's suppose we have a system where there's a platform that is connected with two spring which is connected to ground, and let's say an excitation was applied onto that platform. Let's call it to be in the positive x direction. So how we can write down the equation for this one? So for this one, we know that F equals to kx. Let's say you apply the force F that was applied here, and then just draw the second step is just draw the free body diagram for this one. That is, the force was applied in this direction and it was opposed by the spring 1 and the spring 2, right? So you can, and let's say the downward direction was positive x-axis. So before solving any mechanical vibrating system, making any mathematical model, try to must define the convention for yourself, which direction or will be positive and which direction will be negative, and then stick to it throughout your calculation. Otherwise you will end up getting confused. So the first we define that towards the bottom there's a positive x-axis. So let's say this force is going towards the bottom, it is positive, minus fs1 minus fs2. Since system is in equilibrium, is equal to 0. There's no more unbalanced force. So, or you can call it F equals to fs1 plus fs2, and then you can substitute this spring force, that will be k1 for the spring 1 and k2 for the spring 2. K1x plus k2x, or you can write it as the total net force would be that will be k1 plus k2x, or you can write it as F equals to k equivalent x. So from this example we can conclude that in a mechanical vibrating system, if the springs are in parallel to each other, so their combined stiffness will be the sum of individual stiffness. So no matter how many springs you have in parallel, so the k equivalent will be equals to k1 plus k2 plus k3 plus k4, so on and so forth until kn, right? Now let's say those springs are in series. So let's say we have a spring here, then another spring here, and this is K1, this is K2. Now let's say the force, this is positive x-axis, that's positive x-axis, and now because they both are in series to each other, so their displacement are not connected to each other directly or perfectly. You can take the example of if you tie the two elastics together and tie one end of the other elastic to the wall and just try to pull it. So the first elastic that is in your hand will be in tension more than the second elastic, right? So it shows they both will not have a uniform displacement. They both will have different displacement. It means that they have independent coordinates. So the first one will have, let's say, x1, second one is vibrating, has independent coordinates, displacement coordinate of x2, which they are not dependent on each other. So now, so what do we do here? We have to, since we know that the spring force is F equals to kx, and since they both have the independent displacement coordinate, so the total displacement would be equals to x1 plus x2, and we can substitute from here. We can know that s equals to F over k, so that x will be equals to the force of spring 1, sorry, it will be equals to the F over k1 plus F over k2, and you can write it down as f x equals to F into 1 over k1 plus 1 over k2, or you can write x equals to F into k1 plus k2 divided by k1 k2. So, and that is the equivalent spring stiffness for the series. So from here we know if the springs are connected in series, the equivalent stiffness will be equals to 1 over k1 plus 1 over k2 plus 1 over k3, so on and so forth until 1 over kn. It tells us, so whenever you find a mechanical vibrating system where the springs are, some are in parallel, some are in series, so for all those who are parallel you can find the combined equivalent stiffness like this one. For all those springs which are in series, you can find the combined stiffness coefficient or constant like this one, and then you can further solve such system. So take the example, let's say just try to solve one of the system which has both. So now we have a system which has both of the series and parallel. Let's say this one that's connected to the ground, and we have spring another one, and then we have another spring, and then it's connected to ground. So let's call it K1, let's call it K2, let's call it K3, right? So here we know that there is a displacement in this direction called x. That is same for both K1 and K2. But since K2 and K3 are in series, so they both have a difference in their displacement. So what do? We define a node in between, and we call that another coordinate. Let's call it y. And now let's suppose a force is being applied from this direction. So we can draw the free body diagram for this one. So how this will look like. Let's suppose draw here. So we have a force in this direction. So, and let's suppose we have a positive towards downward and negative upwards. So it is being opposed by the spring force of first spring and the spring force of the second spring. right? But at the node 2, because by the Newton's third law, uh, this will have an opposite effect onto the node 2 like we have discussed previously. So it will be Fs2 for the second spring, and then we will have the third spring that is pulling it again, opposing the applied force, Fs3. So we have a, let's say you can say a second spring like this one. So that's a free body diagram for this system. So now we can draw the equations. So the first equation for this part will be F, that is positive, minus Fs1 plus, oh sorry, minus Fs2 equals 0, or F equals to Fs1 plus Fs2, and we can directly write it as, let's just leave it here in this for the equation 1. For the equation 2, we will have, let's say, Fs2 in positive direction, Fs3 in negative direction, so Fs2 minus Fs3 equals to 0, and so second spring force would be equals to the third spring force. So if we just start writing the, plotting the formula of the spring force, that will be K1 x plus K2, that will be the x minus the from the subtract the y from the x, x minus y, that will be the net displacement of spring 2, because x is the total minus the y, because that part is not covered by the spring, second spring, so that is x minus y. And for the, again you can write this one as K2 x minus y equals to K3 y. Now the next thing what we'll try to do is try to eliminate the unknowns as much as possible. So just try to simplify this one. Try to eliminate the y, so to reduce the number of independent coordinates, so that we know what we can do here. So next thing would be, so we have to, the next thing would be we have to eliminate the extra number of coordinates so that we can simplify. So just try to open up this one, k2 x minus y, sorry, k2 x minus k2 y equals to k3 y, and you can take the k2 y on the other side. The k2 x would be equals to k2 y plus k3 y, and we can take common, that is k2 plus k3 k2x, and the y is equals to k2x divided by k2 plus k3. Now we can substitute this y in equation 1, or call it equation A. Substitute y in equation A. So that would be equals to f equals to k1x plus k2x minus k2, and multiply by this one, that will be k2x over k2 plus k3. So if we take x common from all of these, so it will be x k1, sorry, k1 plus k2 minus k2 square divided by k2 plus k3. So that's our equivalent spring constant in case of a combination of the parallel and the series springs. So this is how the similar thing you can do for the damper. Let's say you have a parallel damper. So let's say you have, sorry, so you have a damper like this, and second damper like this, and that's let's call it B1 coefficient, B2 is a coefficient, damping coefficient we have, and we have because it's not connected to wall anywhere, so we have an independent coordinate called y, and we have another independent coordinate called x. And now if you apply the force in this direction, let's assume the force in this direction is towards positive x-axis. So now we should be writing the equation of motion for these all of these. So at this node, if I write it like this one, at this node, if the force is applying in this direction, so there will be opposition by the damper FD1 and FD2, right? More appropriately, if you call it D1 and D2. And we know the damping force is equals to F is equals to uh, d x dot velocity, and that is a damping force. So we can write the equation of like F minus fd1 minus fd2 equals to 0. So now we can substitute the equation of damping force into our governing equation. So F minus fd1, which would be equals to y dot minus x dot, or you can call it x dot minus y dot for them. That will be sorry, that would be d1 x dot minus y dot minus d2 x dot minus y dot, since both are parallel to each other, equals to 0. Or you can take common for them, x dot minus y dot d1 plus d2 equals to 0, or f equals to d1 plus d2 into x dot minus y dot. That's an equivalent damping coefficient. You must be thinking why I didn't define any wall here. So damper mostly obviously doesn't exist individually all alone. So damper exists where there's a spring or the mass, and it is actually an opposition to the movement of mass or the extension of the spring. So if there's no spring or the mass, what's the point of having an opposition? So damper is always present where there is spring and the mass in the system. So that's why I draw it as a part of system, continue part of the system, not like connected to the wall directly, like not connected to the wall, rather it's a part of system somewhere at the back. That's why we have defined as an independent coordinates for the dampers. So this is how you can write down the equation of motion for the damper one, and I would like you to try the series coefficient for the dampers in series. Try to find the equivalent coefficient for the dampers in series. Maybe we can try one. So yeah, you can write this one as the equivalent damping, right? Or the equivalent, you can say. And so it tells like for all the dampers in series, the equivalent would be equals to d1 plus d2 plus d3. Maybe sometime in our course we might refer this as c equivalent, c1 plus c2 plus c3. Different books have represented it in a different way. Some call it by c, some call it by d. It's just an abbreviation. So I would expect you to try the series one, and then just let me know in the next lecture. Uh, Maybe we can try the series one ourselves, and then you will try the combined one. So let's try the series dampers in series. So let's say we have again a part of a system. We have a damper here and we have another damper here, just like here. So in this case, what we are going to do, we have an independent coordinate here. Let's call it y. We have an independent coordinate here. Let's call it x. Let's call it d1. Let's call it d2. Now since they both are in series, they won't be having an equivalent displacement, equal displacement. So there has to be an independent coordinate in between them. Let's call it z, just for our ease. So the force would be equals to, so if the force acts in this direction, that's the positive one. So that 4, if you draw the free, we have to draw the free body diagram for this one. So at node, just call it A, node B and node C, that's node. So at node A, if the force is applying in this direction, this damper will be opposing that force, and this force, this damper will be exerting some force onto the second damper at node B, and then second damper would be resisting that force, right? So we can write it as F equals to FD1. I'm just doing it quickly, and since FD1 is equals to FD2, so it is also equals to FD2, right? F is equals to FD1 and FD1 is equals to FD2. This is how we can write it directly. So that F is equals to D1, that is Z dot minus X dot, because it's, let's suppose it's moving in this direction, it will be Z dot minus X dot, and it will be equals to D2 y dot minus z dot. So it's moving in this direction for y dot minus z dot. So here the z is the displacement of a point between damper 1 and damper 2, because the same force is transmitted through these. So now we can simplify this one. So we can simplify this one. You can just write it d1 z dot minus x dot is equals to d2 y dot minus z dot. So we just try to eliminate the z, the extra coordinate we introduced for our solution. So d1 z dot minus d1 x dot equals to d2 y dot d2 z dot. And I hope you know the meaning of dot, that is d over dt, that is d over dt of x. So we call it x dot. Here it's z. So just take z dot on other side. So we have z dot equals to d1 plus d2. Just take it on other side, that is d1 x dot plus d2 y dot. So that will be d1 x dot plus d2 y dot divided by d1 plus d2. So now this can be substituted into our original equation, and we can find out the remaining, and that will help us to determine the equivalent amount of damping in our system. So now we have to substitute this one into our original equation. Let's call it A. I should have named it before. Okay, now we have to substitute the z dot in our equation A. So we can substitute as F equals to, where we are, so F is equals to, let's write it as F is equals to d2 y dot minus z dot. So we can substitute this z dot into this equation. That will be equals to F equals to, choose any of these, F equals to d2 y dot minus d1 x dot plus d2 y dot divided by d1 plus d2. So this is what we have now. So we can write it as F is equals to d2 y dot minus d1 x dot divided by d1 plus d2 plus d2 y dot divided by d1 plus d2, and then we can take y dot as common. So it will be equals to d2 plus d2 over d1 plus d2 y dot minus d1 x dot divided by d1 plus d2. So that's what we have here. Uh, and then you can take it as uh, the LCM for this one. That will be d2 square plus d1 d2, and then it will be plus d2 divided by d1 plus d2 whole into y dot minus d1 x dot divided by d1 plus d2. And then you can take this as common, as 1 over d1 plus d2, and then we have again d1 as common. So it will further complicate this one, or we can easily redo it. I apologize for this step. Just erase this part. So once you substitute this into this one, let us substitute this one. So just write it as f equals to d2 into, yeah, just take an LCM for this one, d1 y dot plus d2 y dot minus d1 x dot plus d2 y dot, that's whole equals to d1 plus d2. And we will have, yep, we will have this one f equals to d2, that will be, so this will be minus, not the plus, minus d2 y dot. So it will cancel out this one, cancel out this one. So what we will be left with will be equals to d2 d1 y dot minus d1 x dot divided by d1 plus d2, and you can take this as common. So d1 d2 divided by d1 plus d2 into y dot minus x dot. So this is an equivalent damping coefficient for our system. That's an equivalent damping coefficient for our system. So I will just give a tiny example of finding the equivalent system damping coefficient for the combined parallel and the series one, which you can try on your own. Now jumping towards mass spring damper system. So we just try to discuss some basic terms today, and then we'll move towards the next one. So that is lecture. So let's suppose you have the mass spring damper system. You have the mass here, and you have a spring connected to the ground, and you have damper connected to the ground, and you have the ground, and it is being excited, yeah, and with a free vibration, and let's call it to be positive x-axis, and it is a mass, it is excited, and it's under the free vibration. So you can draw the free body diagram of this one. So the first step you take is draw a free body diagram. So M would be equals to, if it is excited towards bottom, so there will be resistance from the spring force, from the damping force, or just call it Fs and Fd instead of 1, and obviously it has some inertia as well. So you can write the equation of motion for this one, that will be mx double dot, because if we assume that the system was excited towards the bottom, and if it is moving towards the bottom, the inertia of the body is acting opposite direction, in the opposite direction. Inertia always acts opposite to the direction of motion. So if you take downward as positive, so the upward will be negative. So minus mx double dot minus fs minus fd equals to 0, or you can take all of them on the other side. So it will be mx double dot plus fs plus fd equals to 0, or mx double dot plus kx plus cx dot, just call it dx dot equals to 0. Let's rearrange this one, mx double dot plus dx dot plus kx. That's a standard form to write this one, equals to 0. So that's the name of this equation will be a homogeneous second order ordinary differential equation. So why it's called homogeneous? Because there's nothing on the other side of the zero. It's a free vibration. There's no external force acting. Otherwise, it will be non-homogeneous equation. But this one is homogeneous. It's second order because we have a second order here. We have a double derivative involved in this equation, and it's ordinary differential equation. We know there are two different differential equations. Primarily, one is ODE, and other one is called the partial differential equation. So partial differential equation where in all of these cases mx double dot means m d over d square over dt square of x, and dx dot means d equals to d over dt of x. So all of them are being differentiated with respect to time only. So if there was a equation where the coordinate is differentiated with respect to time, with respect to other coordinate as well in a single equation, then that will be the partial differential equation. Means not that time is not the only thing that is differentiating the equation coordinates. Rather, there are other factors too, based on which we are trying to study the difference of equation with respect to time. So that's the homogeneous second order differential equation. So now that's the standard form of the equation. For our purpose of studying the mechanical vibrating system, we try to normalize the equation. So normalize the equation means we try to get the equation in the form of uh, uniform terms that can be used to classify the mechanical system or the dimensionless quantities. So in this case, we divide the whole equation by m. It will become x double dot plus d over m x dot plus k over m x, right? So now substitute here. This k over m is actually equals to omega square, and this d over m is equals to 2 into damping coefficient. So this omega square, if you just write it as omega first, so omega dot would be equals to under root of k over m, and that's 2 lambda simply equals to, or the damping coefficient equals to d over 2m. So this represents natural frequency of any mechanical system, and that's a damping coefficient. So why do we need to divide by the m and get this quantity? See, because whenever you're studying a mechanical vibrating system, you are interested in what is the natural frequency of the system, because you know whenever the force that is acting onto the body, the frequency of that force matches the natural frequency of the body, it will undergo resonance. You must have studied in high school physics. So resonance, sorry. So whenever the external force frequency matches the natural frequency of a body, it undergoes resonance. So whenever you're designing a mechanical system, you don't want any of the external force coming near to the natural frequency, because you know when it goes resonance, it will vibrate with very high amplitude, and it will ultimately rupture. Let's say you have a bridge, like this one. So, and the wind is blowing over the bridge. So, if the wind is causing a certain frequency of vibration in the bridge, but if that frequency comes nearer to the fundamental frequency of the bridge or the natural frequency of the bridge, let's say it was 12 hertz, so it means the bridge will start to vibrate at a very high amplitude, and ultimately it will fracture, it will fail, it will destroy the bridge. So that's why it is important to study the natural frequency of every system, because we are not interested in individual value of x and individual value of k or d. They are telling us nothing. We are interested in the physical interpretation of these values. So the physical interpretation of these values are this, the natural frequency. So these quantities help us to find the natural frequency of our system. Same in the case of the damping coefficient. How? So, so I will explain why do we need natural frequency. It tells us how fast does an undamped system vibrates. That's why we want to study the natural frequency. And why do we need a damping coefficient? It tells us how fast will the vibration damp out or diminish, right? So both of these have physical interpretation. They will help us to understand the system physically, what will happen in the real world, not just numbers. They are helping us to find out how quickly the system will vibrate, or how quickly the external vibration, if we apply the force onto the external vibration, how quickly, if the wind strike the bridge, how quickly the vibration of that bridge will stop, because everybody wants the bridge not to vibrate. So we are interested in how quickly it will vibrate if I add this amount of damping. So if it is less, we will think of adding more amount of damping, so that we want the bridge to quickly stop vibrating. So that's how we find the mathematical model, and that's how we find the these normalized forms. So we can rewrite the equation as x double dot plus 2 damping coefficient to delta, or damping coefficient x dot plus, you can write it as omega square into x equals to 0. So that's the general characteristic equation, the general equation of motion for a mass spring damper system. Or you can want, if you want to elaborate further, it's a single degree freedom of mass spring damper system, because we are studying only in the x direction, we are not studying anywhere else. Although our topic is not the solution of this equation at the moment, we will discuss that, because there are different ways to solve this one. But just for your understanding, I will solve this one, so that whenever we are discussing these things, you have a complete picture of what we are trying to do. So, so there's a different method. The first method is for solving this one, or more appropriately solving this equation, because we have to decide at this point which method we are going to use for solving this system. So there's a differential equation method, or you can call it a standardized approach. There's a Laplace approach. We are going to be interested in these two. There are other approach to the energy and work based approach, so there are other methods as well. So today we are going to look into the standardized approach, because we need some elaboration for the Laplace one. So that's a single degree of freedom, second order homogeneous equation. So the general solution for the second order homogeneous equation is x equals to ke lambda t. You can call anything k, a, b, c, you can call it AE lambda t, you can call it BE lambda, just a constant value. We don't know at the moment what's the value of this k at the moment. It's just a constant value. Maybe you must have studied this in calculus. So that's a general solution of, I'll write it as general solution of second degree of freedom equation. That's x equals to ke lambda t. So it means x dot, the derivative of this one will be equals to k, and because it's a constant it will come out, that will be lambda e lambda t, and then double derivative of this one would be equals to k lambda square uh, e lambda t. Now we can substitute this x dot x and x double dot into our equation here. So let's call it, so we can call it x double dot would be equals to k lambda square e lambda t plus 2 delta damping coefficient, and that's x dot into k lambda e lambda y lambda t plus omega square k e lambda t equals to 0. So e lambda t is common, just take that out, and we can write it as, and the lambda is also common, sorry, k is also common, so it will become lambda square plus 2 damping coefficient uh, plus lambda plus damp natural frequency square equals to 0. So from this equation you can see either k e lambda t equals to 0 or this equation is equals to 0. We call this solution that we have solved this system. So either this equals to 0, we call it trivial solution, means not important, not important, yeah, you can call it useless. We are not interested in this solution, we are more interested in this system of finding these values. So that is a system, that is a part of solution that we are interested in, so that is called as a characteristic equation, because it is determining the character of a system, or characteristic polynomial equation. And now we know it's simple quadratic equation, so we can find the roots of this quadratic equation by lambda will be equals to, if you apply the famous quadratic formula, it will be equals to minus delta plus minus iota, that's imaginary number, omega square minus lambda square divided by yeah, we don't need to divide, we have already divided that one. Or if I just don't want to write it directly, just lambda equals to minus 2a, that is plus minus iota 2 into a, that is 1, here it is 1, under root omega square b square minus ac divided by 2a. So minus b plus 1 minus b plus 1 under root b square, that is 4a square minus 4ac, and yeah, it will, where it is, that is 2 uh, delta square minus 4, a is 1 and c is omega square, that's b square minus 4ac divided by 2a. So we can further simplify this one, minus lambda plus minus, we'll just take this out, that's extra 1, so it will be 4 lambda or delta square minus 4 omega square divided by 2, and you can just substitute this one. When 4 comes out, it will be 2, and 2 will cancel out each other. You can write as delta square minus omega square. Uh, that's the solution for this one. So once we reach the this roots, we are able to find obviously we have two roots. One would be equals to minus lambda plus iota delta square minus omega square. Other would be equals to minus damping coefficient minus of iota damping coefficient square minus omega square. So we have two roots. We can substitute that one into our equation of motion, and we can solve that equation. So we can have the generalized solution for our equation would be xt equals to k1 e lambda 1t plus k2 e lambda 2t. That's all the theory from the theory of the calculus. There's nothing mechanical vibration exclusive mechanical vibration theory. That's all the calculus theory that we are discussing here. So here we can substitute the values of lambda 1 lambda 2 and just start solving. Find out values of k1 k2. Obviously we will need initial conditions of as well. Let's say x at 0 equals to x t equals to 0, and x dot of 0 equals to x dot at t equals to 0, so on and so forth. So that after substituting all of this, we will have some values of k1 and k2. And once we have the value of k1 k2, we can resubstitute back into this equation and find out and report the final solution. Let's say that becomes 5.24 e lambda 1 is, let's say, 2t plus 2.54 e 3t. So that will be the general equation of our mechanical vibrating system. So you can plot this one with the time and x, so how this system will vibrate with the time. That is one of the method to solve the mechanical vibrating system. There's a lot of to this theory, and how we can use these these cases to find out, because again, this is all the pure calculus theory. We are not interested in the solving the mathematics. What we are interested in is finding the physical interpretation of this, like we were interested in finding the physical interpretation of this equation, and we did so using the natural frequency and the damping coefficient. So in this case, we will look into how we can utilize these roots and try to understand what are the effects of different values of roots onto the physical interpretation of our system, for trying to find out whether I have designed a too much damp system, or my system is very less damp. Should I increase the damping? Because the mass is not in our control easily. The spring constant is not in our control most of the time. What we can control is how damping we can add or remove. So that's why we analyze the system based on the amount of damping. So that's all for this lecture, and we will discuss the solution further. That is the physical interpretation of these roots in terms of mechanical vibration. But before that, because we need to discuss imaginary number and the real number quickly, and the Laplace transformation, and then we'll jump to the further explanation of this lecture. So I hope so you understood how we can proceed, how you can use this mathematics to understand the physical explanation of these systems. So I will give some assignment for this week, and that is just for your practice. There's no marking for that, it's just for your practice. That how such that you can learn how to make the mathematical model of different scenarios. So I hope so you understood this subject so far. It's a lot of mathematics involved, but if you apply or think practically, it is really interesting, and it's core of the mechanical design. So should you have any question, you can write me an email or drop me a message on WhatsApp. I hope so I'll be helpful to you. I hope and you guys are safe. I mean, Assalamu alaikum.